we're going to say some words, very few words, on the analytic resolution of nth order linear ordinary differential equations. So before, when analyzing first order linear ordinary differential equations, we said that the analytical resolution in general is quite complicated and very few equations could be actually solved analytically. Here, as you can imagine, the analytic resolution of, in general, nth order linear ordinary differential equations, it's much more difficult. So here we're going to center the case, the analysis, on second order linear ordinary differential equations in order to be more specific. And this is the most general form, the most general expression for the second order linear ordinary differential equation. It's second order because the maximum order you have for the time derivative of the wave function is the second order one. And it's linear because the y function and the derivatives, they don't have any power on the wave functions and its derivatives. And as it's second order, in order to specify the result, we need, besides equation, we need in this case not one, as we had in the case of first order linear differential equations, but here we need like two initial conditions. In general, one is related to the function itself, and the other one is related to the time derivative of the y function. So, as we have said before, in general, these equations are really very difficult to solve, and actually most of them, they don't have analytic resolution. That's why it's very important to have the numerical analysis, because in principle we can always make a numerical analysis for any kind of differential equation. But I think it's maybe interesting to say some very few words on some specific cases of the linear order differential equations. So in order to do so, we are going to center our analysis on a specific case of second order differential equations, which is the one that has these coefficients which are multiplying both the wave function and the derivatives are constant coefficients. So these are the ones that the case that we're going to analyze here. So this is the most general expression for the second order linear ordinary differential equations with constant coefficients. This is the equation again, and this is the initial condition. And in this case, we can say some words on the analytic resolution. So the first thing is that first we have to center our analysis on the homogeneous equations, which is the one where h is equal to 0, which is this equation, p times second order time derivative of y plus q prime plus sy equal to 0. This is the homogeneous equation, and we're going to try solutions of the following type. We are going to type solutions of these exponential solutions, exponential solutions over a times rt, where r is going to be a constant, t is the independent variable, and we have to we are going to plug these type of solutions here in the homogeneous equation in order to be able to determine which is this r constant that determines the solution for that type of equations. So that's what we are going to do, and we're going to plug this kind of solutions here. We're doing that. You have p times the second derivative of that. When we plug this exponential here, it's going to be r squared times t plus q r rt plus srt. As in all the cases you can see appeared exponential, so you can simplify it, and exponential eliminates, and the equation that this R here coefficient satisfied is this one, is P square plus Q times R plus S equals 0. So this is the equation which is actually called the characteristic equation that we need to solve. The second order equation is to solve in order to determine the R constant that's going to specify the solution for the homogeneous case. So this is what we need to do. So we need to calculate the to solve the characteristic equation, which is the one we do have here. And we might have two different cases. We might have that and two different cases. One, the one where the roots of these equations are different, and the one where the roots of these equations are the same. So we just have one R. In this case, the general solution for the homogeneous case is this one. We have the combination of the two types of these two exponentials. And as this is, and this, so you have a general combination of these two exponentials. So there's a general constant times this exponential plus another constant times this exponential. And as this is the solution for just the homogeneous case, so this is going to be equal to 0. So we have to add another term that's going to determine the particular case where the non-homogeneous solution. In order to have that extra contribution is associated to the solution when the equation is non-homogeneous. So you have, instead of 0, you have an edge. So when instead of 0 you have a constant here, the solution will be this one for the homogeneous one plus this extra term that appears because you do have, that's not going to be 0, but it's going to be a constant. So this is for the case where the two roots are different, and for the case where the two roots are the same, we do have like this other kind of solution. And as you can see here, there are two unspecified two constants, C1, C2, we're calling both cases. And that's why, in order to specify the exact, the precise values of these two constants, we need to go to the initial conditions, these two initial conditions. So we do have these two initial conditions in order to specify the values of these two constants. So these two constants can be obtained in terms of these two initial conditions. It's also important to mention that these roots, they don't need to be real. They can be imaginary numbers. And these imaginary numbers are also allowed to appear here in the exponential. And whenever we have an imaginary number as a root of the characteristic equation here, I think it's important to have in mind a very interesting, a very useful equation, which is a MOV equation, which basically says the following. I'm going to write it here below. E to the E times alpha, where alpha, let's consider it's, in this case, alpha is a real number, and this I is the imaginary number. It's equal to the cosine of alpha plus I, the imaginary number, times sine alpha. So the exponential of the imaginary number can be also written in terms of a cosine and a sinus. And of course, it's going to be an imaginary number as well. But as we have like two imaginary numbers, we can combine these constants in a proper way so that the solution could be also real. So a real solution can be written in terms of two different imaginary exponentials. So again, if the roots of this characteristic equation is imaginary, it's also allowed, and we can write the general solution in terms of two imaginary exponentials. So basically what we have done here is we have considered an analytic solution of very particular case of a second order equation with constant coefficients, which actually it appears sometimes. It's very kind of common equations and could be useful in order could be useful to be and to be able to solve these kind of equations in order to check if the numerical methods that we are playing with and actually it's actually going in the right direction or in the wrong direction when we're working with them.